Right. Hey everyone, thank you for joining us today. It's been a bit of a hiatus. We're back now. This time it's a pretty interesting topic. So, I think company-wide, Red Hat, IBM included, there's a lot of interest all the way up to the CEO on how do we tackle the uncertainty in sort of, broadly speaking, agentic systems, but then language models, components like the reward models, PRMs, and so on and so forth. And so we were actually, the way we stumbled upon this work, even though it was done in-house, was one of execs, the IBM side, actually reached out to me 2 weeks ago saying, hey, they've seen this paper that talks about the calibration problem in process reward model. And I'm going to leave all those terms to be explained by the speaker. But they sent me the paper and they were like, there's this work that does this. Like, read the affiliations. And then they're having that, how was in the work. And the young guys have been with us before at the MIT IBM lab. So he's going to talk about that today. And just a quick intro, Youngjin is an amazing PhD student of Navi season over at MIT. He's been working with us for I think a year and a half. Advanced learning was where he started, and then has done a lot of work on understanding uncertainty, different aspects of uncertainty. Okay, so with that, I'll give it over to Youngjin to just have a topic, all right?
Thank you so much. Thank you everyone having me today. I'm Youngjin Park. You can call me Youngjin or Youngjin Young. Anyways, yeah, so today I'm going to go on a presentation of this amazing work. Jointly collaborate with the Hao from Red Hat, and also MIT IBM Watson, Christian, and I'm working with Navid. So as in title, the key, some of the keywords would be the test time scaling in large language models for reasoning task, and the process reward model. And calibration is something that we make this happen. And just another thing is we make this inference time scaling or test time scaling in an adaptive manner, which I will explain more. So let's start how we made it. Okay, so it's been a little bit while, but DeepMind, OpenAI, wins gold medal in 2025, a few months ago. And yeah, so LLM is getting smarter and smarter, and now even they can solve really hard mathematical problems. What makes that happen? Of course, one of the reason would be the training time scaling. So this is something also human does. So as we grow up, we learn more and more, so that we can, when we are in elementary school, we can just solve really easy math. But and then we grow up, we solve calculus, and we probably can even run physics. So like this, if we spend more training budgets for models, for example, we can use larger models, larger data set. Of course, we can make models better. However, training computes reaches to some capacity, and we cannot scale it up anymore. We can scale up more, but it has some challenges. So another perspective, in addition to this training time scaling, is something called test time scaling or test time compute scaling. The basic idea here is if we use more test time compute during inference stage, we can even make this LLM even more smarter. So it's good. How can we achieve this test time scaling? One way is chain of thought. So I typically say this is more deeper way of thinking. So rather than LM to give the answer in a one shot, let LM to think one step reasoning, 2 step, 3 step, and multiple step to yield a final answer. So by doing so, we would use more token generation tokens, but it will reach to the better answer. However, there are some problems regarding this approach, which is that longer chain does not guarantee the better solution for every time. It reaches to some good level of accuracy very quickly sometimes. So like not for every LM, of course, but as shown here, some LLMs actually degrades when you use more test time compute in terms of from the perspective of chain of thought schemes. So another test time scaling approach people recently are working on is like more like broader or wider thinking, which I call, or proposer and verifier scheme. So the left figure shows the one example how to do that. So rather than ask LM to generate an answer, we use this LM as more like policy LM. So this policy LM generates multiple candidates of answer, and then we introduce another LLM, which people call as verifier or reward model, so that this reward model scores each candidate answer generated by LLM policy. And for example, they can choose the best among this n solutions, or they can like majority vote. They can do like weighted vote. Like they can do basically do a lot of things. But here, as you can see here, how people use more test time compute here is like wider. They generate more samples, and by doing so, they could achieve better solutions. In this work, we will focus more on this type of test time scaling. More specifically, we use like two like approach, which is first one is very popular approach based on n. So as you may all know, they generate multiple candidates and select the best one at the end. Another more sophisticated way to do this test time scaling is bin search. So rather than waiting for LLM to generate the full answer, we make LLM to generate just first step reasoning and then pause there, choose the top K best one, and from those branch we proceed another reasoning step, expand and choose another top two, right, like top K and so on. So by doing so, we can get a more promising trajectories compared to the best of n. So these are just some good examples how we can do test time scaling for LLMs to make them smarter. Surprisingly, this test time scaling could boost up the performance of LLMs. So for example, here the blue one is the 1B model, and the x-axis is the budget, inference time budget. And as you can see here, 1B models can surpass 8B models when more test time compute is used. And also, likewise, 3D models, which is aligned with the orange color, can surpass even like 70 models, 70 models when enough test time budget is used. So far, like I advocates the test time scaling is good, really good, but I need to raise this question. Like, more is better, but would you really scale that? Like test time compute, even for solving like easy question like what is like 1 + 1 is equal to what? Thanks, Gemini. So like I don't want to use this. For example, here they show like I don't want to use like 10 llama models for just solving these easy questions. And one reason is that like I don't want to waste my compute. I don't want to use like O3 Pro model for these kind of easy questions. So yeah, be smarter, not harder. That's the first keyword I want to focus on. So yeah, this is very similar to how humans think. So for easy problem, we do a quick thinking. For difficult problem, probably we collaborate or we take more time and we solve it. But if we fail to do so, which means that if we do a quick thinking for difficult problem, then probably we will likely to fail. Whereas if we if you collaborate, like if we collaborate everyone to solve very easy research question, then probably just a waste of like time and effort. To this end, our solution was instance adaptive scaling. So let's scale adaptively based on the instance. Here the instance is like question and reasonings. Let's get deep a little in more detail. So for each step, we will scale by this. So here the step is question and partial reasoning. So in the initial step, we only have question. So now we have question. And let's think about the beam search. And we proceed one reasoning step. And question, and for each reasoning step is a like endpoint. So here this n is a scale we want to, the number of computes we want to allocate. So basically this is asking like how many budgets are we gonna use for after each step. Let me get more deeper. So here the C is just desired accuracy, just like fixed parameters. So like if you want to guarantee like 90%, then you can just like fix 0.9 or 99% more conservative settings than 0.99. So it is fixed. It is not adaptive setup. So the more important part is P. So that we define P as a probability of LLM eventually yields a correct answer given a question and partial reasoning up to T step. So let's say in the best of n approach, there is no reasoning step, so it is only condition Q question. For easy question, LLM is likely to yield a correct answer, so P will be higher, will reach to 1.0. For difficult question, LLM is less likely to yield a correct answer, so P should be more close to 0. So it is around 0 and 1. So this is just a quick graph showing the relationship between N and P. So higher P, we use less N, less budget, and lower P, we use higher budgets. Of course, in practice, in our practical algorithm, we just cap this N so that we be sure this N does not blow up, does not assign thousands of candidate generations. But yeah. So this is the overall kind of idea how we solve this problem. And before we go another detail how we actually achieve this, this is some result we get. So this x-axis is a budget ratio. So 1.1 is 100%, so it's just a fixed budget. And for example, 0.3 on the x-axis is 30%. They just use 30% budget on average. And y-axis is accuracy, so it's higher, it's better. The blue dots are the accuracy and budget, so it's normalized, so it's 100%. They use fixed budget, 100%. For each model, they achieve some accuracies like this. And the star is our final algorithm. As you can see here, the accuracy is very comparable to the original test time scaling scheme, but it can save the budget up to 67%, for example, just by adaptively scaling. So just avoiding scaling up too much on easier question, for example. Coming back to this scheme. Okay, it's conceptually looks good, but how can we estimate P? Because the P is the key indicator deciding factor that decide this and how much we want to scale or not. So the first shot we tried was process reward models. So this process reward models is a special type of supervised reward model that gives a score or verifies given a question and partial reasoning. So let's take a look on the left example. Let's say these are step-by-step reasoning steps, and input question and prompt. Let's call the numerator parameter X, then PRM outputs some score. And also, if you put question along with this another reasoning trajectory, then also give us score. So how this PRM is used in test time scaling, for example, in search is question, they generate n candidates, score them, as mentioned, and then we can prune like too low value, like the trajectories with too low values, like too low scores, because it's not promising trajectories anymore. The process reward models actually is doing, we can like regard this process reward model is actually doing something we initially want. So we can we imagine like process reward is estimating some notion of this success probability of LLM. However, yeah, so can we trust PRMs? And yeah, we found it is not true for different reasons. There are, yeah, probably there are many different reasons, but the key problems we wanted to raise is that PRM is often used or trained to rank better. As mentioned in the beam search, PRM chooses a good answer over the bad answer, worse answers. So if they rank the candidate answers in a correct manner, then that's fine. Which means that, let's say they choose 0.5 because it's the highest, where they reject 0.134, it's good. But it would work even PRM outputs like 0.8 on the correct answer and 0.157 to the rejected scores. In other words, the reward is not always calibrated with respect to the success probability, which we actually need for instance of adaptive scaling. So like PRM is not designed, probably not designed for a good like for this like success probability, although it's outputs some scores. Another more important problem is PRM is trained with like some LLM policy model. Let's think about one PRM model. They use like not only they use a human annotator, so human is the LLM policy, and also they use like Quen 72 models, which is really kind of strong in mathematical reasoning. So they use those LLM for policy model. But if we, for example, if we use this PRM for 1B model, then it's not different, which means that even though the success probability of some question and reasoning was like 70% for Quen 72B model, it could be just like 30% for like very weak 1B llama model, or even it could be like 99B model for I don't know, like 400B models, right? So the generic PRMs isn't like, yeah, it's not tailored to my LLM. So there's really low chance that it could be calibrated to our purpose. But that's this like two point of view is the like evidences we had about why it's PRM are not likely to be calibrated. So this is more like empirical like, numerical analysis we have done. So let's take a look at it. So the x-axis is the estimated reward by PRM subtracted by success probability. The other, so here the success probability, the ground success probability, we measured by rollout. I will explain more later, but just now just take it as a ground truth value. So if this value is positive, then this reward model is estimating the success probability in a like, more optimistic way. So it's overestimating success probability. If it's a negative value, it is underestimating the success probability. So for different question and the partial reasoning like pairs, we compare this ground success probability versus the reward model value and draw this density plots for the Quen model on a Math 500 data set, Quen model or AMI data set, and Shepherd PRM, another like prominent PRM on Math 500 and Shepherd on AMI. And as you can see here, like especially for difficult challenging out of distribution tasks like AMIs or like for Shepherd and even like Quen PRM, you can see there's like they're skewed on the like the right side. So this is evidence about existing PRM is overestimating their success probability. So yeah, we know calibration is poor, so we wanted to solve this problem. Okay. So the proposed method is the uncertainty over.
Can you go back to the previous slide again?
Oh, sure.
Here, can you talk a little bit more about how do you calculate these? Are these on intermediate steps?
Yes.
How do you get the? I mean, how do you know the ground truth? For this.
Great. Yeah. Actually, that's something I just wanted to mention in the next slide.
So, sure. I mean, if you're covering it, then it's good.
Just quick answer is that we just roll out and just count at the actual ground probability. I can show you. Yeah.
Yeah.
Maybe ask me later again, like if you don't understand. So for each question, like we random sample the question from Met 500 training set. This is not probably in Met 500, but let's say this is one of the example. We ask LLM, the target policy LLM, to generate some partial reasoning. We just paused in some intermediate steps. And then for given this question and prefix, we roll out roll out the generations from that prefix until to the answer. So here, for example, it'd be like 1 plus 1, let sum be x. First, then x is 2, x is 3, x is 2. So at the end, after rollouts, we can actually count how many answers were correct over the whole n generations. So in this case, 2/3 is correct answer. So we take, okay, so for given question, for this prefix, the success probability is 0.67. You need to also note that we use this target LLM, so which means that this calibration data set should be generated for each target LLM. So we generate this question prefix probability for Llama 1B model, and also like Llama 3B model, 8B models, and Quen 7B models, and different models. It should be generated in different manners. I mean, in the same manner, but in like different LLMs. And we also like put those calibration data sets into the Hugging phase. After collecting this calibration traceability data sets, we fine tune the off-the-shelf PRMs like Quen PRM with LoRa fine tuning. But more importantly, we do this by quantile regression. The quantile regression is so if you think about PRM, they just give the scholar score, just one score. But estimating score itself is not. It's actually a challenging problem. Like there's some uncertainty, like in estimate we are as well. So rather than making PRM to just like predict just single value, we fine tune the PRM to, for example, in our case, generally like 10%, 50%, and 90% quantile. So like for example, 10% quantile means that it's kind of like a lower. You can think of it as a lower bound. So the score of the reward is likely to over this value with 90%. Like 50% is a median and 90% is like upper bound. It's kind of upper bound. So this is another like conceptual diagram. So given input question and reasoning prefix, the existing PRM will output just like overestimated reward, a single value 0.95. But we calibrate the PRM with our collected data set with a quantile regression manner. So it will, rather than output a 0.7 only, it will output like 10% quantile, 0.6. Oh, okay, so it will be larger than 0.6 with 90% confidence, 0.7 or 50%, 0.8 with 10%. The good thing about this quantile regression is that we can use these different quantiles based on our needs, which means that if you want to more conservatively scale which means that we don't want like a conservative scale, then we will use 10% quantile because it will like the reward is likely to above this value anyways. We didn't have tested, but if someone wants to like save the budget very aggressively, probably someone wants to use maybe 90% quantile, like 75% quantile. But like in our experiment, our goal was more like preserving the accuracy, but we want to save the budgets for especially for more confident and easy questions. So we use this 10% quantile value when we do this instance independent scaling.
I'm gonna ask the question again. I don't think I fully get how you. What I understand what you're doing is you have some ground truth type setting where you're able to say if I roll out k samples for each of k answers for each of the questions, and I know the final answer is wrong in say a subset.
Yeah.
I will use that as my data set for calibrating.
Yes.
But I mean, so the thing that I'm not saying that it's a good strategy, but do you account for the fact that oftentimes it is very likely that the first k minus 5 steps were actually exactly correct and similar in all the chains, and it was the very last step where some mistake happened, right? Because I mean, this is an amazing way to calibrate an ORM, but a PRM, is it a mechanism in your method that accounts for the fact that error might have happened in the very last step? Because now if you're, does that make sense?
Yeah, I get the point. But we roll out for every each intermediate steps. We interrupt the intermediate step and we roll out. So it's all those kind of business. The chance of failure is is considered into the success probability.
So the prefix can be like a half reasoning.
Half reasoning, or just the first reasoning, or even the last k minus 1 reasoning.
But how do you verify if that step is correct?
So given the prefix, we roll out from that k minus 1 prediction.
Right, but I suppose what I'm trying to understand is like accuracy of a step is not always in some rollouts very likely that a correct step led to rollouts that ended up in incorrect answer. Right? And I'm just trying to understand, we account for it because okay, I want to say this, like if you were telling me you were calibrating the ORM using this, I would be amazing. Like, this is great. This is how we should do it ORM. Where I'm not able to connect the link is, and I'm going to reiterate what I said, is it's very likely that if you look at the K rollouts, that all of the first 10 steps were correct, right? But the steps after the 10th step,
Yeah,
right,
can be wrong.
can be wrong.
Yeah.
Right. So in your in your calibration method, how would that reflect in terms of like, are you gonna penalize? So say I have 3 rollouts, right? Like, and they all had very similar correct answers, and the very let's just make up an example, right? I'll make an example. I'll say like there are 10 steps to a problem, and all 3 rollouts were correct until the 9th step, and 1 was wrong in the final step. When I calibrate the PRM, I expect it to say, yeah, all 3 were correct, right? And as long as it lowers the score for the right one, right, I'm good with it. Just like so, what I'm trying to get to is that how it would look?
If I understand, so
The way so let me phrase it, because I think this example might have worked. So if in the extreme case where the chain was exactly identical until the k minus 1 step, what you are really doing is you're basically getting a score, expected score for this chain. To say this chain, 66% of the time leads to the right answer, right? So if this is the chain, your scoring for intermediate steps should be around that the second quantile, right? It shouldn't go over 66. Is that correct? Is that what I'm like? If that's
Yeah.
is that what I mean? Is that what's going to happen? Because
Yeah, 60%. Yeah, 60%. Yeah, that's true. Yeah.
right. Okay. I wanted to go to the math a little bit more. Like to me, that's what calibration would mean in this case. That
Yeah.
this trace, which is correct, completely correct.
Yeah.
In expectation, only gives you 66%
Yeah,
accuracy.
exactly. That's the definition, and that's how we call it, right?
And so the scoring now for the traces, even though they're right,
Yeah.
should be around 66%.
Right. Exactly.
Okay.
Got it. Yeah. So that's a good point, because that's one of the biggest difference between the existing PRM versus like our calibration PRM, because like PRM typically when they train, like they measures more the reliability of the given prefix. So if this prefix is correct, then it's just one.
It's a very interesting problem because I know that you call it calibration of PRM, but it's calibration of PRM with respect to the uncertainty in the language model,
Yes.
in the policy,
Right.
Because
Yeah.
the PRM is doing the right thing. It's
Yeah.
saying this is
Yeah,
right. I'm
exactly.
going to give it 90%.
Yeah.
But I need to somehow account for the fact that the policy can misfire on the correct trace and give you a wrong answer.
Yeah. That's actually the really important part why we need calibration.
That's cool. That's very cool.
Thank you for pointing out, like, yeah. So after calibration, we could observe this overestimating problem has been resolved very significantly. Maybe someone can ask that how about just use like temperature scaling or isotonic regression is to be like very standard calibration techniques without like ease of fine tuning. And so here, this is a graph comparison study. The purple one is the quantum regression based calibration method. The blue one is the original uncalibrated PRM. Calibration error, lower is better. And as you can see here, unfortunately, our finding is a simple calibration technique cannot resolve this issue because this is a more complicated problem. It's not just LME, PRM is overestimated, like 10% overestimate, on average, overestimate or like underestimate. It's more like based on an LLM. Sometimes it needs to the context agnostic. So the calibration should be understand the question and the reasoning with respect to the LLM, but that should be take account for which this temperature scaling or isotonic regression or those methods could not be done. So so this kind of like context aware calibration techniques, like thermometer work, like those kind of work, like it should be like is essential for our calibration purpose. That was another key takeaway we learned from these experiments. After all, now we calibrate PRM, so we can say PRMs now know what they don't know. And now we can better trust PRMs. I would skip, but just like saying that there's some in practice we just kept some the budget by some fixed and so we calibrate PRM as I shown before we could save the budget very significantly. So this is another example. Experiment I show. So the second column is uncalibrated PRM. So this is original PRM. If you use this uncalibrated PRM for this IAS framework, since it overestimates the success probability, especially for like 1B models, a weak model, they will shrink the budget too aggressively for all the questions. As a result, they just allocate just one, like, or one or two, three budgets on the question for every question, and end up being the accuracy is sacrificed too aggressively. However, if you take a look on when you use the calibrated PRM, you can see that the accuracy is very comparable. While we could just use budget like up to like 30% or 20%. Another interesting you can take a look here is that this amount of budget saved is adaptive to the LLM. So the first row, 1B model. 1B model, they should not save budget too much. So they use a 63%. But for like our R1 distill model, like their stronger model, say B7B, so they save budget up to like 70%. They usually use 30% budget. Similarly, when it goes to the challenging question like Amy data sets, they did not save budget too aggressively. They actually spend like more like maximum budgets because they think this is very difficult question. See the accuracy is just like 10-20%. So they should, it is the expected result. This results with the best of n IAS. When we apply IAS, some scaling on best of n, we saw very similar results when we apply this IAS on the beam search. And there's another diagram showing the effectiveness of IAS. So x-axis is the number of samples we use, and the different color shows a different level of questions. So level 1 is the easiest one, level 5 is the most difficult one, and the star is the budget we used for when the IAS apply, and the accuracy is known the y-axis. So you just need to like left to right, because as you can see here, the accuracy drops because it's a more difficult problem. But you can see they use more budgets as the difficulty is the problem is getting more difficult. Same for 1B, same for 8B. We will observe the similar trend for different models. You can see in the paper. So so this is all showing why the calibration is important, and not only just for trustworthiness. If you calibrate with PRM correctly, you can also use that for a effective budget savings. And now PRM calibration equals IAS. That's the main message I wanted to deliver.
A quick question. What is your 100% budget on those graphs?
Oh,
Is it like 2:5 or more than that?
we use up to 64. 64. So like 64 was the maximum budget. It's both IAS and fixed budget that use.
I see. And then you do like 30% of that number.
We need extra labels to the quantile regression, or what exact data is.
Oh, so the good thing about quantile regression is the quantile regression loads does not need like the quantile label, of course. They just need this triplet, question, prefix, and focus probability. This quantile loads just optimize these three values based on so that the output value can match the mathematically to 10%, 50%, 90% quantile. So you can think like this. So for 10% quantile, the loss penalize when the actual value is lower than, like, penalize more when the actual value is lower than the expected value. So like
How do you you only have the mean there?
so it's like you can just think about how much do we penalize. So for 10%, when you when we calibrate with 50% quantile, then we penalize equally for overestimating, underestimating. But when we make LLM PRM to predict 10% quantile, then we need to ensure it should not like we should like guarantee that try to make the predict value is not higher than the actual value.
Yeah, I get that.
Yeah.
But how
So the
So
weight
you
is
penalize.
separate. So they weight like 9 times more, for example, for like underestimating the overestimating for 10%, vice versa for 90%. If you are more curious, you can actually, it is on the paper, but weighted quantile loss is very,
Basically, you know them. Like for example, the about 25%. So if that's the case, the 25% is about the mean. With the max you are shallow and 0 is like, and you can see the loss here.
so like, well, yeah, I motivate this quantile loss more from like time series forecasting, which I have done before. So in like time series forecasting is really uncertain, so they typically do quantile regression to the point estimating. Yeah, I naturally just thought it is more desirable for PRM calibration.
We do. I think data only has the success probability, but your model, the PRM architecture will be different. Usually the PRM has a like a we output a single score to 0, 1. And now you ask the PRM to output 3 scores. Each one corresponds to the model 90%.
You use that lot. Because I was thinking, technically, because your mean is estimated through Monte Carlo, you can technically bootstrapping estimate the quantiles directly. You can send data.
Oh.
It makes a mean. So I was, I thought you
Oh,
might
got
use
it.
that. But yeah.
I see. Yeah. I think ideally saying if we can roll out like 1,000 rollouts, then probably that's very better estimate. Unfortunately, our case due to the like computational budget, like we just roll out just 8 samples per trajectory. So there was also some kind of uncertainty in the label itself, so we didn't exclusively think about the labeling quantile. But I think that's also very doable in our case. So thank you all. So this is going for again like with Hal, Christian, Kabe, and Labid. And thank you so much. Any questions?
Yeah, we have a question online. If you want to unmute yourself, you can ask Misha.
So I just wanted to ask this. A few things here sound terribly interesting, but reproducing the training pipeline is a bit of a high bar. So I wanted to ask if if there are any frameworks or models that are online from your research and could be tried.
So let me just clarify the question. So are you asking about future issues when we develop?
I think that it's asking if like the way you trained your prediction model, is that script available? Is that stuff available to help people do that?
Oh, the PRM calibration. Good question. Yeah. So maybe the caveat here is that PRM should be calibrated for each LLM, target LLM, policy LLM. So if there is a fixed policy LLM you want to use, and if you have some good amount of data sets, then you can do that. But another thing maybe you notice is that we need another rollouts for specific to get this reward model. So if I would say if there is a PRM model in the domain of the application, then I think we can do because a PRM is also trained with rollouts. But if the application is somewhere like non-mathematical reasoning, which means that even whether it is correct or not, measuring it correct or not is difficult, or like preference alignment or something like that, then probably this PRM calibration itself is not. It may not be very, maybe challenging. However, this IAS, this framework is itself is also theoretically derived. And so if you can at least have some good notion about whether this LLM is going to fail or not, given question and partial reasoning, then I believe this framework or the concept can be directly used. But yeah, just to make sure you are estimating a good probability.
I think Youngin has also released his code on his GitHub repo, so we can share that.
Oh yeah.
And also the data.
Yeah, sure.
So any
The GitHub repo would be great, but ideally, I actually wanted to see a Hugging Face if there is one. My question was even simpler. My original question was even simpler than that. Are any models that you trained available to try out before one even tries to rig up the process?
Like, have you released your calibrated PRMs?
Oh yeah, we released the calibrate PRM, calibration data set, and also the code. So yeah, it's ready to go.
Well, thank you very much. I would just very much appreciate the links.
Thank you. Yeah. To be honest, so we are also like ready for the camera, ready for NeurIPS publication. So I think the current code works. I double check, but I will update within a month. So maybe
one question I have is, have you applied this out of the box for like other domains, specifically like so one thing we found is weird, it's very strange. Well, it's not very strange, but it's the strangest thing. Math PRM, they tend to work well on other numerical fields. Just out of the box. Right? If there's numerical aspects, because I mean, if you really think about what a PRM is doing, it's unlikely that it has memorized saying what a good step is. It's a very hard problem. So all it is doing is some kind of, this is my hypothesis, don't take it as, but like if I gave you a math problem and you wrote 13 steps and there were like 20 steps to go, there is no way for even a human to say this is absolutely correct, right? In general, it's very, like, all I can do is I can follow and say logically, if I knew some principles, you are not making a mistake in your logic, right? And if that's what a PRM is learning. It's not learning in math domain, it's just learning if logically derived steps are correct, then technically it would transfer to most domains where intermediate steps are logical, sort of the steps of some that follow some logic. This is a hypothesis, by the way. So I'm not saying this is correct. This is a hypothesis, and what we have found is that this seemed to transfer to other non-maths, but not mathsy, but numerical fields.
got it.
Right. So what I wanted to ask was, have you tried applying it to anything out of the box?
Yeah, I think that's really good point. Like we can try that because when I fine-tune PRM on Math 500 set, I was worried that would it actually generalize to other like math question like AB data set, like, but it did. So I think your intuition is correct, and it's really promising.
There's one other domain where this can be like extremely valuable is tool calling. So when language models tool call, the uncertainty spikes like more than you would imagine. So if you look at the actual sort of meta studies around where agents fail, 60% to actually almost 50 to 65% failures are for its inability to find the right tool. And then 10 to 20% additional is for finding the right parameters for the tool. And it's not that it doesn't work. It works. But it's very inconsistent. It's primarily an uncertainty issue of the policy model. So if you rolled out a bunch of it, your accuracy can go from 60% to 90%. I mean, we have evidence for it. I mean, we have, a bunch of other people have. And there's some other work that also show that once the model receives the tool call, the first token it generates is like super high entropy. And I'm wondering, like, that may not even require a PR, to be honest. That is an ORM issue. But a similar IAS strategy could be like incredibly helpful.
Yeah.
Right? That automatically adapts. The other thing to also maybe think about is like a lot of these things are deployed in production, right? And they generate data continuously, right? Which means it's an ongoing aspect of calibration that you can do on actual real rollouts, right? And that, yeah, that would be another aspect to think about.
I would probably even take a step back, ask like what training data you for is calibrating around. Because I think the first question would be how robust. Like for example, as you said, like we can take that PRM and work it and let it work in other numerical domain. But when we fine tune or when we calibrate this PRM, we just fine tune the PRM using as data set and still make it well calibrated using numerical.
Yeah.
Yeah.
Yeah, I mean, that's what I was trying to say. Now that you have calibrated a map, how does it work on other domains? That's what I was trying to understand.
And the easier question is the second point you mentioned, which is kind of continue deploying the model.
Yeah.
Because then you can collect more in-domain data. But I think those are
Yeah, really interesting questions.
I think it's like agents are being deployed, right? And they are being rolled out. And what they actually do collect is trajectory level, end-to-end response, thumbs up, thumbs down. And if your method can, one thing I was trying to understand is, like, I know that you took a PRM and you fine-tuned it. But a question that I'm more interested in is like, if I took a reasoning capable model, I just want to use your method to calibrate it, do I need to start from a PRM? Why do I need to start with a PRM if I have this method?
Are you asking about like, whether there's another?
So assume any reasoning-based model is capable of finding scores. Right?
Oh,
I mean, I can take GPT-4 and use it as a judge. Right? And I can also use it as a judge for intermediate steps.
I see.
Right? Have you thought about just calibrating?
Oh, so you use same policy model, but we can
You can use
calibrate.
the same policy model, right? Or you can use like a bigger, anything that is reasoning capable, I think can technically be used.
That's true. Maybe really a related note, I also saw a paper at DipCom from Meta. So they use the LLM confidence score, and like they rate with like top K and like tail K and variety of things. But basically, what they claim is the LLM confidence score, even is really kind of like simple and intuitive, but they can still use at least reject some bad results. So I think if you calibrate, probably the confidence score itself is not.
I was thinking about that when I said this thing, because I think your method, you might be applying it on PRMs, but I don't see a reason why it can't be applied to like
we can
any LLM directly.
every kind of yeah.
And so then applying it on tool calls becomes actually possible because you don't have to pre-train it on an extensive corpora of the domain.
Sure.
As long as you have rollouts on like limited labeled rollouts on the domain itself.
Oh yeah, I think it's really promising. Good idea.
Any other questions? All right, thank you. Someone?